I guess so, you know. Gina, do you think he's suffering a lot?
I was going to ask you about the MATLAB. So I made, so how is it rated? I made code where it's just like, you do this operation, it gives you like answers. Is there like a format? I read the sheet and didn't give a format for the code. So
there's no prescribed format for the codes.
Okay. Yeah. To show the results.
Okay, folks. So before we get started, let me just remind you. Oh, Renee, you're here today.
Yes, sir, I am.
That's awesome.
Thank you.
How's it going?
It's going great.
Yeah?
Yeah.
Good. I'm glad. Did you miss us?
Yeah, I did.
Yeah, because we missed you.
Oh.
Like, personally, yeah. So I think everybody's aware of this, but just to remind you, Monday, what's happening on Monday in biotransport? Term test 1, right? Up to the end of Navier-Stokes, so not including Bernoulli, but definitely including all the way up to Bernoulli, right? 2 questions, open book, etc., okay? And you can expect to see stuff from pretty much the whole part of the term up until that point, up until the end of Navier-Stokes. So, there will be, I can guarantee that you will see a control volume on there. You will see Poisson on there, etc., right? So, I can't put every element of the course into 2 questions, but you kind of have to study the whole shoot and match already. And then what's on Friday in biotransport next week? MATLAB project, right? Who's finished their MATLAB project? You finished it.
Yeah.
Anybody else? Okay, 1 person has finished. Has everybody started their MATLAB project? I'm seeing yes. Okay, good. So y'all should have seen that yesterday. Brett sent out an email with a pretty extensive list of office hours. So if you're a little stuck on your MATLAB project, I would definitely recommend you talk to Brett. He's a really awesome TA. Not as good as Gina, of course, but it's like he's still up there on the awesomeness scale. Okay, so yeah, it's kind of a hectic time in biotransport. So let me just remind you that we finished Navier-Stokes and we started into Bernoulli's equation. And I want you all to remember there's 4 big assumptions that underline Bernoulli's equation. So there's Bernoulli written in that box in yellow. And it's basically saying that the pressure, the elevation, the z of a fluid particle, and the velocity of a fluid particle have to obey a certain relationship that you can interpret in terms of a conservation of energy statement. And that holds if the flow is steady, incompressible, along a streamline, and lossless. And of those 4, lossless is usually the hardest one to figure out. And that basically means that you can ignore the effects of friction. And we'll talk more as we go along about when you can and cannot do that. All right? Are there questions about Bernoulli's equation? I mean, compared to Navier-Stokes, this is a walk in the park, right? No derivatives, no integrals, no blah, blah, blah. It's just, straight up algebra. So that's why everybody likes it, but, just remember, not always true. So are you good with Bernoulli, at least in terms of understanding what we got here? Point 1 and point 2 are 2 locations along a streamline, right? That's what those subscripts mean there. So whenever you see a 1, that means evaluate the pressure, the Z, whatever, at location 1. And when you see a 2, means do it at location 2. Right. All righty, and then we were doing this example of flow through a stenosis. And the idea here is that you have a narrowing down of the cross-sectional area. That means that the fluid has to speed up based on a conservation of mass argument. And if you think about Bernoulli and we neglect Z changes, then basically Bernoulli says that the sum of pressure and a half rho V squared has to be constant. So if your V goes up, your P goes down. And so really the question is asking us, what is the pressure at this location in what's called the jet? So the fluid kind of focuses down, it comes through the throat of the stenosis, and then you have a high-speed jet of fluid that comes out through that and kind of goes down the center, and as you go further and further downstream, that jet spreads out. Right? That doesn't mean that there's not blood up here. Obviously, there is blood up here and here, but that blood tends to just be kind of sitting there, kind of swirling around a little bit. It's not kind of in the main flow, which is where the jet is happening, all right? So what we're going to do is say, okay, well, we're going to try to use Bernoulli here, and I'm going to ask you to believe me for now that this flow is kind of lossless. So there's no such thing as a truly lossless flow in biomedical engineering, but we can approximate it as such. It's not such a terrible thing to do. So that's one of the 4 assumptions underlying Bernoulli, lossless. Definitely blood is incompressible. Rho is constant for blood. It's along a streamline. Well, yeah, I can do that. And you notice that I put a 1 and a 2 here. And this is kind of like drawing a control volume. This is part of your gym whenever you have a Bernoulli, is that you will actually on your diagram draw a point 1 and a point 2. So draw a 1 with a circle around it and a 2 with a circle around it. And I will give you points for that on your exams if you identify your 2 locations that you're going to apply Bernoulli between. Here it was obvious, but trust me, in some problems, just like with control volumes, it's not so obvious where your point 1 and your point 2 should be. And so that's so we're clearly along a streamline. That's our 3rd assumption. And then the 4th assumption is steady. Now, that's not a great assumption in this case. Obviously, blood flow in the arterial system is not steady. And so we shouldn't really apply Bernoulli here. And however, I will tell you that it's done all the time in the clinic because it's an easy, fast thing to do. And, doctors like easy and fast. And it turns out that, yes, you make a mistake by applying Bernoulli to this unsteady flow, but you get something that's close-ish. So on this one, just kind of hold your nose a little bit and pretend that the flow is steady-ish. And we're just going to go with it, all right? So now, as you probably deduced from the little intro there, a key part of this whole argument is that we have conservation of mass. And if we're going to talk about conservation of mass, we're going to have a control volume. So let's draw a control volume in that looks like this. Something like that. So it basically encloses the jet. It starts upstream of the stenosis. And in this flow, since it's incompressible and we're treating it as steady, we can say that Q at 1 equals Q at 2, which means that V1A1 is equal to V2A2. And remember, I said that this was a 90% stenosis, which means that A2 is reduced by 90% compared to A1. Right? You lost 90% of your cross-sectional area. And so that basically tells us something about the ratio of V1 to V2. So, in other words, 90% stenosis implies that A2 is equal to only 0.1 times A1. Alrighty. Now what I'm going to do is, yes?
When you're drawing your control volume, do you have to include the 2 points?
Yeah, you know, I probably should have made that control volume come all the way out to 2 there. I'm sorry, I was bad. Yeah. Thank you for catching me on that. Now, what we're going to do here is neglect changes in Z, because, you know, it kind of looks like, I guess that stenosis is somebody who's lying down or something like that. So Z1 is going to be equal to Z2. And in that case, Bernoulli's equation takes this form that says the pressure at 1 plus a half rho V squared at 1 equals the same at 2. And remember, we want to get the pressure at 2. This is what we're interested in knowing. What did they tell us in the statement of the question? They told us the pre-stenotic pressure, 90 millimeters of mercury. So that's the pressure at 1. So that's a known for us. That's good. Let me just get this all onto the page here. So this guy is known. They told us that the pre-stenotic mean blood velocity is 40 centimeters a second. So that's V at 1. That's known. The density of blood rho I can look up in a book somewhere. It's 1.05 grams per milliliter, so just a little bit denser than water, not too much different than water. And V2 I can get by using that set of relationships there, right? Specifically, I know that V2 is equal to V1 times A1 over A2. And I know that ratio of A1 to A2, it's going to be 10, right? Because of this expression here. So this is 10 V1. So that's known. So basically, I know everything in that equation except for P2, which is what I want to know. So I just plug in and I go to calculator land. And let me just show you the steps. So just a slight rearrangement says that P2 is P1 plus this difference in velocity terms here. Then I use my conservation of mass equation here. So you notice that what I've done here is I've factored out a common V1 squared. And then this ratio of V's I can replace with a ratio of A's based on conservation of mass. Now be careful. You notice that, and this is a common mistake that students make when they use Bernoulli, if I have V2 over V1 here, I have to have A1 over A2 here. It's the other way around, okay? So you turn if it's 1 over 2, then the area ratio becomes 2 over 1 and vice versa, right? So just be a little careful about that. But then all I have to do is plug in numbers here. Now, the only thing I have to be a little bit careful about here when I plug in the numbers is you notice that I gave you the pressure in millimeters of mercury, but rho and V are in centimeters, grams, seconds. So I'm going to have some incompatible units in there, and I'm going to have to do a units conversion, right? So sorry about that. And the units conversion that I did, I decided to put everything in dynes per, or my pressure, I should say, in dynes per square centimeter. What's a dyne? Who remembers what a dyne is? Anybody remember a dyne? Yes, sir.
Gram centimeter per second squared.
Gram centimeter per second squared. It's a baby Newton, right? Yeah, so just like the pressure in SI is a Newton per square meter, the pressure in CGS is a dyne per square centimeter. How many dynes in an atmosphere for massive bonus points? Anybody know? Yeah, 101.3250, right? So you got 101.325 pascals in an atmosphere, and there's 10 dynes in a pascal. 10 dynes per square centimeter in a pascal. So it's just 10 times as many dyne per square centimeter in an atmosphere. Okay, so when I plug in all the numbers, I get this pressure in dynes per square centimeter, and if I convert that back to millimeters of mercury, that's what I get. Please, please, please go through this yourself at home. Just make sure you can get those numbers. The numbers are correct. All right. So is the artery going to collapse? Is the pressure in the artery downstream of the stenosis less than atmospheric? No, it's not. Remember, we're working with gauge pressures here. All right. So could I get a pressure less than 0? Yeah, I could, because look at this. If I look at this term here, A1 is bigger than A2. Right? Like I go from big to small, so A1 is big, A2 is small. So the ratio of A1 to A2 is some number bigger than 1. I square it, so I get some number even bigger than 1. And then I subtract it away from 1. So actually, this whole term here is negative. Right? So I'm starting off at some pressure P1, and then I'm losing pressure to get to P2. And so I could easily make P2 be negative by making that second term there larger in magnitude. So for example, I could have a bigger A1 over A2 ratio, which would correspond to a tighter stenosis, like a smaller throat. Or I could have a bigger V, so higher velocity is going to give me a more negative pressure at station 2. So actually you can have negative pressures, and the artery does tend to collapse, which is actually really bad for it. It's another reason that you don't want to have stenoses. Okay, questions about that? Yes?
So if we hadn't neglected the stiffness of the artery, we would be comparing the P2 to the pressure exerted by the artery.
Yeah, so you'd have to do some kind of a solid mechanics calculation. Perish the thought, eh? That would be painful. Other questions? Okay, so I mentioned that we're going to talk a little bit about this whole business about lossless, and I just want to introduce to you something called the Reynolds number. So there was a guy called Reynolds, and he was famous, and he was so good at fluid mechanics, he got a number named after him. That's how you know that you've made it really big time in fluid mechanics, is when you have your own number. Reynolds has his number, and you are going to get to know the Reynolds number in a way that you're going to become very familiar with the Reynolds number over the course of the term, right? For right now, I'm just going to tell you that if the Reynolds number is bigger than 1, much larger than 1 actually, then the idea of lossless is good, right? And when you calculate the Reynolds number for this case, it's 570. So that's quite a bit bigger than 1. And so we're going to say, yep, that's an okay thing to do, is to assume lossless. Now, I realize that that's a little bit unsatisfactory because you're not really sure what the Reynolds number is, and you're not really sure why it has to do with losses. But just kind of bear with me on that, because we're going to introduce that, over the next week or so. Okay? Yeah.
So why does it say in the next sentence, this is really a bit...
Yeah, well, so, you'd like it to be like, 1,000 or a couple thousand, but it's like, it's okay-ish, Let me just say, we made 2 mistakes when we did this. Mistake 1 was assuming steady, and mistake 2 was assuming lossless, right? Of those 2 mistakes, probably the steady one is the worst one. Yeah. But it's just such a nice formula, you just got to go with it, right? So, your other choice is you solve the Navier-Stokes equations for that flow. Yeah, don't go there. Yeah. Actually, there is no solution for that flow. It's too complicated. All right. Next question. Next example. So this is a good brain teaser. I have like a curve in a pipe or something like that, or in a tube. We're going to assume that the flow is incompressible, steady, and lossless. So as soon as you hear that, you know, those words, especially lossless, so the word lossless should make you think Bernoulli, 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 right? So I have this steady, incompressible, lossless flow, and I have a uniform velocity profile at the inlet. So basically, if I draw the velocity profile, it looks like that. Right. My question is, and it's a simple question, as I go around the bend, does the fluid travel faster on the inside curve or the outside, or is it the same? Does everybody understand what I'm asking here? Some of the fluid goes around on the inside of the bend, some goes around on the outside. I want to know at which of those two paths is the fluid going faster? Right. Shall we have betting? Let's have betting. What do you think, sir? Faster on the inside or outside?
Outside.
Faster on the outside. Why is that?
Because more distance to...
Yeah, it's obvious, right? Like it's got a further distance to travel, right? So, you know, if you're going to go around, you've got to go faster, right, to keep up. Yeah, it's like the guy who has to run on the outside of the track. It's always, you know, that's why they run on the inside at the Olympics, right, when they do the long distance things, right? What do you think, Gina? Outside or inside?
I feel like the answer last time was the opposite of what I thought.
She says she feels like the answer last time was the opposite of what she thought. But what did you think last time?
I probably thought outside.
You probably thought outside, yeah. Yeah. Who wants to bet? It might be the same. Want to wager? You sure? I could be wrong. I could just be messing with you, you know. I could be. Yeah. What do you think?
I also think it's outside.
Outside? Do you want to bet?
Not really.
No? Come on, you got to have courage, you know, like faith in your convictions.
What are we betting?
What's that?
What are we betting?
Whatever you want.
Great.
I'll put my house up against whatever you got. Okay. So you know from that it's faster on the inside, right? All right, what do we got here? I want you to think about, this is actually a little bit complicated because we're going to have to do two steps here. First step is we're going to use the Euler-N equation, and then the second step is we're going to use Bernoulli. So Euler-N equation, first step, which, by the way, the assumptions for Euler-N are basically the same as Bernoulli, except along a streamline. If you remember, Euler-N was about crossing streamlines. So Euler-N says, well, we got it right here. It says that d by dn of p plus rho gz is minus rho v squared over r. Now, it doesn't seem like that's very useful, but here's what I want you to do. First of all, step one, what direction does n point in? That's the first thing we got to get square here. What direction does n point in? Anybody remember what we decided last time? It's normal to the streamlines, right? But we got two choices here. It could go, sir? Yeah, always goes towards the center of curvature. So n, that n direction is like this, all right? So that's the first part. Now the second part is, in that right-hand side, I got a minus rho v squared over r. V is the speed of the fluid. R is the radius of curvature. We're not actually given anything, but one thing I can say for sure is that rho is a positive number, v squared is a positive number, and r is a positive number. So that ratio, rho v squared over r, is positive. I've got a negative sign here, so I can tell you that the whole right-hand side is less than 0. So this part here is less than 0. Okay, that's nice. What I'm going to do here, and I can't remember if this is in the setup of the question or not, but we're going to neglect changes in z. So imagine that this thing is lying on a tabletop, so all the z's are the same. So really what this equation says is that dp dn is less than 0, which means as I go in the positive n direction, what happens to p? Does it get bigger or smaller? N increases and p decreases, right? dp dn is less than 0. So what does it mean to go in the positive n direction? It means I travel downwards like this. So as I go towards the center of that bend, the pressure goes down. Which means that the pressure here is high, and the pressure here is low. And if you think about it, that makes perfect sense. What's making the fluid turn the corner? There has to be a force to get the fluid to turn the corner, right? We don't have gravity, because we're neglecting it. We don't have friction, because that's what we assumed. So the only force that's making the fluid turn the corner is P. So there has to be more P on the outside than there is on the inside, right? Otherwise it wouldn't turn towards the inside. So I have a high pressure outside and a low pressure inside. Okay, that's nice. How does that help me? Well, now what I'm going to do is I'm going to apply Bernoulli twice. This is a little bit tricky, so just bear with me. I'm going to start here, and I'm going to go to here, and then I'm going to apply the same idea, but this time on the inside streamline. Now the key thing is that I said that the fluids had the same V at the inlet. And I'm also going to assume that they have the same P at the inlet. Right, so they start off with the same energy, if you want to think of it that way. They have the same V and the same P. As those two fluid particles travel along, that sum of V and P energy has to be constant and equal for both streamlines, right? So when I compare, at any 2 points, or any set of points along those streamlines, the energies have to be the same. Right, that's what Bernoulli says. But the P is higher on the outer streamline, so what can you tell me about the V on the outer streamline? It's got to be less, right? If I start with the same energy, P and V energies, right? Outer versus inner. I have a higher P outer, I got to have a lower V outer. So it actually goes slower on the outside bend, which is weird. It's a good thing we didn't bet, eh?
Good thing.
Yeah. One thing you got to do is you are thinking that the fluid has to go around the corner like that. It doesn't. It's a fluid. Do whatever the hell it wants, right? Actually, it goes around the corner like that. It's weird. Yeah. Welcome to fluid mechanics. Questions about that? Y'all good? Okay. Congratulations. We finished local analyses, which is basically hydrostatics, right? Pressure in fluids at rest, buoyancy, conservation of mass, Navier-Stokes, and Bernoulli. That is the hardest section of the course. It's all downhill from here. It's just like falling off a log. It's going to be so easy, right? Just tickety-boo. Isn't that right, Gina? Do you remember that? Yeah. We're going to start on Buckingham Pi Theorem now. And I'll tell you right now that students are very suspicious about this because it's too easy. Right? Let me just suggest to you that when something is offered to you that's useful and easy, in this class you should take it. All right? And Buckingham Pi Theorem falls into the useful but easy category. So here's how it works. When we talk about physical measurements, we have units that are associated with it, right? Like meters, feet, whatever it is. And when we apply laws of physics, like F equals ma, A equals dv dt, then that means there's also units there. But, and here's the key point, the units, the laws of physics existed before we invented the units, right? Like, okay, what's a foot? How did they get the foot? Sorry? No, it was some guy's foot, right? There's a unit of measure in Germany which is like the length from the tip of your finger to your elbow of a certain person. And they used it to measure lengths of rope. And if you go to old medieval German towns, on the side of the city hall, there'll be like literally a metal bracket, which is that unit of measure. I think it's like the L or something like that. I forget what it's called, right? But you know, and we could maybe tomorrow we'll invent a new system of units, but F equals ma before we invented all those system of units. So what that's saying is that any fundamental law of physics that we have is independent of any system of units. And that means that you should be able to write your fundamental laws of physics without using any units. And I know I'm always like crazy about units and everything, but we'll find out that there's actually a really cool way that you can do that. So the first idea that I have to introduce to you is the concept of dimensions. So dimension is an example of a dimension is a length. Right? There's lots of different units for length, feet, meters, inches, centimeters, microns, etc. But they all represent a length. So the fundamental concept there is length. Another dimension is time. So there's different units for time, seconds, hours, whatever, but it still represents time. And similarly for mass. So in this class, we're going to have 4 fundamental dimensions: mass, length, time, and temperature. And the symbol for mass is capital M, for length is capital L, temperature is T. Time is T. We'd like temperature to be T too, but we already used it for time, so we give it theta. All right? Now, you can derive the dimensions of any quantity from those basic things. So what are the dimensions of volume? Well, what's a volume? A volume is a length times a length times a length, right? So the dimensions of volume are length cubed. What are the dimensions of velocity? Length over time. Dimensions of force. Length times mass times time squared, or divided by time squared. Exactly correct, right? Because how do I get that? F equals ma, right? So the dimensions of F are the dimensions of m times the dimensions of a. The dimensions of a, well, acceleration is length over time squared. So if I think about that, I have mass times length over time squared. That's my dimensions of force, right? So this little notation here, if I put a square bracket and a squiggle like that, that means has the dimensions of. So I can put F square bracket squiggle ml over t squared, right? And that's exactly what we do right here as this example. Okay? So nothing complicated there. By the way, when you do dimensions, you don't worry about any numerical constants. So, you know, if there's a pi or something like that in your formula, don't worry about it. Just get rid of it. We only ever end up with m, l, t, and theta. All right? Okay. So the really cool idea is that there are certain combinations of quantities that are dimensionless. They do not have any dimensions. And they're very special, and we call them pi groups. right? And we'll see why they're special in a few minutes. But what I would like to do now is introduce you to your what will become your favorite pi group, which is the Reynolds number. So the definition of the Reynolds number, and this is, we're going to find out that there's different flavors of Reynolds numbers, but for right now, Reynolds number is the density of the fluid. So I want you to think about flow in a tube or a pipe, okay? Rho is the density of the fluid. V is the velocity or speed of the fluid. D is the diameter of the tube. And mu is the viscosity of the fluid. Now, my claim is that this is what we call a pi group. It has no dimensions, which is weird. Right? How would we prove that? Well, we would look and see what are the dimensions of the constituent parts. So let me just write out the definition for the Reynolds number again. It's rho v d over mu. So what are the dimensions of v? Well, that's easy. It's just L over t, right? Length over time. D is a diameter, so it has the dimensions of length. Nothing special there. Rho, it's a little bit more complicated. It's mass per volume, so it's ml to the minus 3. And the hard one is mu. And this is a hard one. Let's say that you couldn't remember the dimensions of mu. What would you do? Well, you would say, oh, I know that the shear stress tau is mu dvx dy. So I would say that the dimensions of mu are the dimensions of tau divided by the dimensions of dvx dy. Right? That's basically Newton's law of viscosity. What's tau? Tau is a force per area, right? Did we already figure out the dimensions of force? It's ml over t squared. So I divide that by area, which is L squared, and I get m over LT squared. So those are the dimensions of tau, m over LT squared. What about this dvx dy thing? The good thing about this is you just cross out the d's. So that just has the same dimensions as v over y. So it's like length per time divided by a length. So that just ends up with inverse time. And when you put that together, mu just is m over L over t. ml to the minus 1, t to the minus 1. Okay, everybody see how that works? Am I going too fast, sir? You good? You could give me the dimensions for anything now, right? You just like break it down into its constituent parts and, work from there. Sir, you good? Yeah, you feel confident about this? Yeah, gentleman to your left. You good, sir? Awesome, okay. All right, so let's see if it works. My claim is that the Reynolds number is dimensionless. So what do we got here? I'm going to take the dimensions for rho. So here's my rho. And that gives me m over L cubed. All right? Then I'm going to take the dimensions for v. That's L over t. Then I'm going to take the dimensions for d. That just gives me an L. And finally, if I don't run out of possible colors here, which I guess I am, I'll take the dimensions for mu, which is our more complicated thing, and that's m over L to the minus 1, t to the minus 1. Right? Just plug and chug. Now look what happens here. You see that I've got an m upstairs and an m downstairs. They cancel. You see that I have a t to the minus 1 upstairs and a t to the minus 1 downstairs. They cancel. I have an L to the minus 3, but then I have another L and another L, so putting those all together, I get L to the minus 1. In the basement, I have L to the minus 1, and they cancel. So I end up with something that has, actually, you can think of it as being, has dimensions of m to the 0, L to the 0, t to the 0. It's dimensionless. We call that a pi group for weird historical reasons. Right? So you know how I have this policy about units on my exams, and if you don't have the right units, you lose 50% of your grade, right? What's the one time that you don't care about units? When you write down a pi group, right? Because there are no units for a pi group, right? So as long as I express my rho, my d, and my mu in consistent units, so let's say I do everything in SI, I'm going to get a number for my Reynolds number in a given situation. If I do it in British, I get the same number. If I do it in CGS, I get the same number. Any system of units I want, I always get the same number. And so the idea is that this is something that existed before we came up with any system of units, and must somehow reveal something fundamental about how nature works. So I always say that nature talks in pi groups. Nature doesn't know that F equals ma, but it knows that there's a pi group called F over ma, and that equals 1. It doesn't know that E equals mc squared. It knows that there's a pi group called E over mc squared, and it knows that that equals 1. All right. So you might think to yourself, that's nice, you know, that and $1 gets me a cup of coffee, right? Well, I'm going to ask you, do you trust me on this? Good. Do you trust me? Yeah, good. I'm glad. I'm going to ask you to trust me on this, but you're going to find out that pi groups are super powerful and super useful, right? Before we can start using them, though, I have to tell you how you get them. Because in a given problem, I gave you the pi group here, but in a given problem, you don't know what the pi groups are. So step 1 is to get the pi groups. Step 2 is to use them. The good news is that step 1 has already been worked out for us. So there was this guy called Buckingham, and I mentioned there's this thing called the Buckingham Pi Theorem. And the Buckingham Pi Theorem does 2 things for you. It tells you in a given problem how many pi groups are you going to get. That's useful thing 1. And useful thing 2 is it tells you what the pi groups are. Who could possibly ask for more, right? I mean, there's nothing else you could ask for, right? You know how many there are and what they are? That's got to be sweet. Do you want anything else besides that? No, I mean, what could you possibly ask for, right? Okay, so here's how it works. And here's how I want you to think about it. So I'm going to come to you and I'm going to say, you know, I'm interested in analyzing blood flow through the aortic bifurcation. And I kind of expect that, you know, the flow is going to depend on the density of blood, the viscosity of blood, the diameter of the aorta, the cardiac output. It's going to be a function of time. It's going to be a function of, there's a stenosis that's upstream, so it's going to be a function of the stenosis size, et cetera, et cetera. So I'm going to come to you with a list of parameters, right? Rho, mu, d, et cetera, et cetera. Each of those parameters is going to have certain dimensions in it, right? So like rho has m over L cubed, so it has m and L in it, et cetera. So here's what I'm going to do. I'm going to make a little matrix here, and all of my parameters I'm going to write across the top of the matrix. So this could be like rho, mu, d, v, etc. across the top. That's just my list of parameters strung out. And then along the side, I'm going to write my dimensions. And for us, most of the time, we're only ever going to have 3. It's going to be m, L, and t. And then a given entry in the matrix, let's say that one there, is going to be the exponent of L in the parameter f2. What does that mean? So let's say f2, oh, I kind of did that badly, didn't I? Well, all right. So let's say that f2 is mu. And you might remember from the last page that mu has the dimensions of m, l to the minus 1, t to the minus 1. So what's the exponent of L? There, it's minus 1. So I would put a minus 1 in this matrix right here. Right? So I basically just go through and I fill up that matrix. So you have to know what the dimensions of your parameters are, and we'll practice this a little bit. All right? That's called the coefficient matrix. And I'm going to suppose that, let's see, what do we got here? I have n of these guys. So I have n parameters. And then I'm going to say that the rank of the matrix is R. Does anybody remember what the rank of a matrix is? I'm sorry to dredge up this piece of linear algebra from your ancient past. I know that's very cruel and unfair of me. Do you remember what the rank of a matrix is? No, nobody ever does. Sir, do you remember what the rank of a matrix is? Some funky thing, right? Who remembers the rank of a matrix? Some shy member of the class who doesn't speak up much. Mr. Breaking Point Audio Productions. What is the rank of a matrix? Ooh, did you hear that? It's the number of rows where the diagonal element in the row has non-zero entry. Right? No, it's not that. Yeah. But you're really close, actually. I think you actually know, but you're just not quite saying it in the right way. Who can help? Taylor, can you help him? This guy here, he doesn't know how to wear his hat properly. He's got it on backwards, but, you know, help him. Do you remember what the rank of a matrix is?
It said number of independent columns.
Number of independent rows. Yeah, the number of independent rows, right? So if I have a matrix with 3 rows in it, the rank could be 3 if all of the rows are independent. It might be 2, or it could even be 1. How do I do that? I do row reduction operations, right? And if I can zero out a row, then by any combination of row operations, then that means that the rank for every 0 row, every row that I have which is all zeros, that means I lose 1 on my rank count, right? So if all my rows are independent, my rank is 3 in a matrix with 3 rows, right? So then the Buckingham Pi Theorem says, hey, look at this. I know how many pi groups I'm going to have. I get it by that formula right there. I take the number of parameters, so that's how many of these guys I've got. I subtract off the rank of the matrix, and whatever that number is, that's how many pi groups I got. So that gives you a target to shoot for, which is good. It's good to have a target. Now, the second part is how do I actually get the pi groups? So, what you're going to do here is you got a whole bunch of parameters and you want to combine them in special ways so that they're dimensionless. When you first look at it, you say, that's going to be hard. So you're going to be a little mean here, right? And I'm going to ask you to play favorites, right? I know you're not supposed to do this because it hurts people's feelings and stuff. But for purposes of this, don't worry about it. We're just going to play favorites among the parameters. I'm going to ask you to pick some of the parameters as what your favorites are, right? And we're going to take that, and specifically I'm going to choose R of those parameters, and I'm going to call those R parameters the core group. And Gina, I think I'm out of time. Am I out of time? I'm getting close. Oh no, we could get another 3 pages of notes in before the end of class, don't you think?
Maybe 1 page.
1 page, 1 page, 1 page. How about we take this up? I guess it's going to be Wednesday next week, right? I look forward to seeing you all in flip session on Friday. And then again on Monday.